Hello everyone, I'm Murshed. I welcome you all to my poster presentation on the study of non-toxic and stable perovskite solar cell materials. Photovoltaic systems are an efficient solution to the rising energy needs of emerging economies and greenhouse gas-related issues across the planet. Perovskites have emerged as materials with the potential to revolutionize the photovoltaic industry with an efficiency of 25.7% achieved just within a decade. These materials have a general crystal structure of ABX3, so choosing different elements for forming a perovskite structure provides a compositional variety. Figure 1 is a comparative efficiency chart made by National Renewable Energy Laboratory, which shows comparable efficiency of perovskite with the established silicon solar cell technology. Pairing metal halide perovskite with conventional silicon leads to a more powerful solar cell that overcomes the 26% practical efficiency limit of using silicon cells alone. These Oxford PV tandem cells are on the run for offering enough extra output to enter the market. Unlike silicon solar cells, perovskites offer less expensive and simple fabrication technique. Most of the recent works in this technology have been dominated by toxic lead-based perovskite. Further development in the commercialization of this technology can be brought by reducing the toxicity level and increasing the atmospheric stability. As a goal of my research, I have chosen cesium as a stable inorganic A cation instead of unstable organic cations, tin as a less toxic B cation instead of the toxic lead cation, and iodine as a X anion to fabricate dicesium tin hexaiodide perovskite and study the influence of guanidinium thiocyanate and pyrazine additives in the improvement of the photovoltaic properties of this perovskite composition. My experimental mechanism to fabricate this material in figure 2 is a simple solution processing by heating mixture of proportionate chemicals and annealing the films in vacuum chamber with pre-established heating time and temperature. Figure 3 represents the structural characterization of the X-ray diffraction pattern of the perovskite crystal structure. Perovskite peaks and impurity peaks are represented by the asterisk and the triangle respectively. If we focus on the first arrow, we can see that both the additives have significantly enhanced the intensity of the perovskite peak compared to the reference no additive sample, which is more pronounced in the guanidinium thiocyanate sample. So we suggest that guanidinium thiocyanate has enhanced the overall perovskite crystal orientation. If we focus on the second arrow, we can see that the intensity of the impurity peak has been significantly reduced by the addition of pyrazine. Our elemental distribution in table 1 show that all of our samples have a ratio close to the ideal composition ratio of 2:1:6 for dicesium tin hexaiodide perovskite. Figure 4 represents the morphological tunability of perovskite surface, where the amorphous regions present in the no additive and pyrazine samples are marked in yellow circle. The guanidinium thiocyanate sample in the most right shows defined grain structure with improved crystallinity, which is very important for the charge extraction capability of the perovskite. Following the favorable results achieved with guanidinium thiocyanate, we have continued our next step with this additive. As solar cell materials are exposed to light and temperature, so it is important to test the stability of perovskite cells under these atmospheric conditions. Figure 5 presents the X-ray diffraction pattern of the perovskite crystal structure exposed to light and dark thermal treatment at 65 degrees Celsius for over 100 hours. We can see a similar pattern after the stability treatment compared to our reference as deposited sample. However, we have observed a slight change in the intensity of the peaks. To further understand the stability of the perovskite films, we measured absorbance that is presented in figure 6, which shows thermally exposed films in dark condition have improved absorbance, while the light exposed films have significantly reduced absorbance. So we suggest that the guanidinium thiocyanate added samples are highly stable under thermal annealing but prone to decomposition under illumination. As a summary, we have successfully fabricated dicesium tin hexaiodide perovskite through the solution processing, and guanidinium thiocyanate enhanced the overall photovoltaic properties and the thermal stability of the films. There are two main challenges that need to be addressed in our future work. Firstly, complete elimination of the impurity peaks from the perovskite crystal structure, and secondly, enhance the stability of the films under light condition. A more efficient fabrication mechanism can help us solving these issues. A broader impact of my research is to provide cheaper, less toxic, and highly efficient photovoltaic solutions to develop the renewable energy sector. That was the end of my presentation. I thank you all for your time.